Assalamu alaikum ji. This is Muhammad Nawan Aslam Khan, and this is lecture number 13 of our course Numerical Methods. Just a recap of what we were doing. We were doing the linear system of solutions, and in a broader sense, we are dealing with the system of equations. Okay, and in the system of equation, we got the linear system and the non-linear system. We started with a linear system and we revisited the famous Gauss elimination and LU factorization with the pivoting strategy. We have seen that there are some actually issues when the diagonal elements are smaller in magnitude. So we identify that particular problem and we try to resolve it through the pivoting strategy. Okay, so um, after doing the Gauss elimination and LG factorization both with the pivoting strategy, today we'll move towards the uh, solution through some more methods of the linear system. But the method we're going to learn today will be the iterative methods, okay? Namely Gauss elimination, Gauss-Seidel method and Gauss-Jacobi method. Gauss-Jacobi method is also called the simply Jacobi method, okay? Okay, so today we'll start in this particular lecture. We start with the iterative methods, okay, namely Gauss-Jacobi method and Gauss-Seidel method. Gauss-Jacobi method is also called simply the Jacobi method, okay. Just a quick overview of the Gauss elimination and LU factorization in a way that when we start a problem solving a linear system through Gauss elimination or LU factorization, we follow a certain pattern and at the end we got a solution. It is very much different as compared to the topic one that we have when we done the system of one variable equation, in that we start from either an interval or from certain initial guess. A guess can be 1, a guess can be 2, okay? And then we build a sequence that takes us towards a solution, okay, up to the accuracy we wanted. So, but if you see Gauss elimination and LU factorization, they does not start with any particular guess, okay? They follow a certain pattern, a procedure, and takes you towards the result, okay. So that's why they also called the direct methods, okay. So LU factorization and Gauss elimination, they are also called the direct methods to solve the linear systems, okay. So what we going to today, and also called the non-iterative methods. So iterative methods are those which start from a certain assumption of a solution. Our initial guess is what is always that possibly it is a solution, okay, and then we build a sequence towards this particular solution. So, but the Gauss elimination and LU factorization are not like this. So they are also called the non-iterative methods, okay, or direct methods. The methods we're going to learn today are called, in general, the iterative schemes for solution of the linear systems, and they also called the indirect methods, okay. They also have the name of the indirect methods. So methods are Jacobi and Gauss-Seidel. Before I go to the Jacobi and Gauss-Seidel method, we have to learn about a norm of a vector. We'll see how it is related with our actually objective in this particular lecture. So we'll start first with the norm of a lecture, then we develop the Jacobi and Gauss-Seidel method, and by the end we will develop the convergence criteria of these two methods. There are possibilities that we're not able to get the solution through these two methods, okay. So we'll be looking that too, okay. So let's start with the first thing, which is um, norm of a vector. And I will discuss why we need it, okay. So let me write an equation, okay. So we know the linear system has this matrix equation, okay. This is the matrix equation of the linear system. Now, in the methods we're going to learn today will be you can draw an analogy with the topic 1 that we started with. Okay, so we'll start from some initial guess. So what this unknown vector is, it can contain some unknowns x1, x2, so on to xn. So these are possible unknowns that we wish to find. Okay, so both the matters that we're going to learn today start with some initial guess. Okay, like for example, the Newton method, it starts with some initial guess. Okay, similarly, this starts with some initial guess. Now, if the system is n cross n and this is the unknown vector, obviously these are all the real numbers. Okay, and this capital X actually belongs to which space? Rn space, because there are n elements in this particular vector. If we got 3 cross 3, then X will be from R3. Okay, so it means I have to assume some initial value of x1, I have to assume some initial value of x2, and I have to assume some initial value of xn. Okay, one more thing that you find in the topic 1 when we start any particular problem, there is an accuracy which we need to achieve. Okay, we usually call it as tolerance. We use this notation to represent it. Okay, so this is the tolerance we wanted to achieve. Okay, so we start from initial guess, we build some sequence, and that sequence take us towards this accuracy that we wish to achieve, towards that solution. Now, once we have this initial guess, let me just write a transpose here to make sure this is a column vector. Okay, so this notation is for the transpose. So for example, this is our initial guess, and after putting certain procedure, I get an answer x1. Okay, so let's say tolerance is 10 is power minus 4 for sake of discussion. Okay, so we, after plugging this input, okay, as an initial guess, I got an updated answer. Okay, let's say updated answer is at the step number 1. So the superscript is actually representing uh, the index. Okay, the superscript is representing an index. Okay, so with this initial guess, I got this updated answer. Now I need to check, as I check in the Newton method or any other method in the topic 1, is it an answer? Okay, did we get an answer? Okay, is this the answer we need to stop? Do we need to stop or not? Okay, for that we have stopping criteria. Okay, let me write over here. We have some, hopefully you remember from the one variable equation, when we have this, the stopping criteria was either we get a point P such that f of P is less than tolerance. This is one of the stopping criteria. Let me write Pi, make sure this is some point in the sequence. Okay, and the second stopping criteria, we also have seen this, that maybe the consecutive terms are so much near, okay, of the sequence, so there is no much difference between the consecutive terms, so we can also stop at that point. By the way, there is another stopping criteria. It's called relative stopping criteria. It is Pi minus 1 divided by Pi. Okay, it is also used as a stopping criteria. Okay, so just for information. Okay, now for example, I need to check, is this a solution or not? So there are two things. One is, let's try to see in this particular scenario which stopping criteria will be viable to use. Okay, so if I have this solution, a possible solution, then the first criteria says plug this into the main equation. Okay, so we will have equations and equations. Okay, we'll plug into the over there, and we'll see either we get a solution or not. Okay, either we get a value near to the vector b or not. Okay, after plugging the values of x, multiplying with a, does it satisfy, is it equals to b or not, is it as much near to b as I wanted or not. Okay, so For example, if we have 3 equations, this may be easy to do. If we got 4 equations, so the computation is more as compared to 3. If we got 10 equations or 100 equations or 1,000 equations, then obviously there's a lot of computation we need to do. Okay, so it means after every iteration, if we got an answer, we need to plug into the equations, okay, and to find a solution, either it is near to B or not. So there will be a lot of computation. Now, if you see the second criteria, okay, it says whenever you got a solution at any iteration, at any point, just check the difference between the previous one and that one. Okay, so if this is the solution x1, if this is the solution, the previous solution x0, we can just take the difference of the two. When we take the difference of the two, let me take the difference of the two, x1 minus x0, and I need to check is it a solution or not. Okay, so what can I do? I need to compare this with the tolerance. Okay, we need to compare with the tolerance. Now you see, tolerance is a real number. Okay, and if you see the solution lies in the n-dimensional space, either R3, R4, R2. Okay, because it's a system of equations, it will be more than one. Okay, so either we got 2 equations or 3 equations or n equations. Okay, so if I subtract these two vectors, still the answer will be in the n dimensional, and I need to compare this thing with the real number. Okay, now to do this, what can I do? Anyone? How can I actually translate this vector into a thing so I can compare it with the it's a column vector. It's a column vector. Okay, transpose will be a row vector. Then I need to translate this into the real number. Okay, so what is this? An absolute or a magnitude of a vector? Okay, when you take a magnitude of vector, what it does? It gives you a real number. What is a magnitude of vector? It is a distance of a vector from origin. Okay, a magnitude of vector is just a distance of that particular vector from the origin. Okay, if you just consider it like this, so it will give you a real number. Okay, okay, vectors are not comparable. You can't say that the vector 1 is greater than the vector 2, or a vector 1 is less than the vector 2. You can only argue about the equality. Okay, you can't argue about greater than or less than. Okay, they are not comparable spaces. Rn is not a comparable space when n is greater than 1. Only at n equals to 1 it is comparable. Okay, so you can't say a vector 1 2 is greater than 3 1. Okay, you can't say this. You can talk about the magnitude of the vector. Okay, magnitude of the vector is greater than the magnitude of the other vector. How do you do that? You translate that vector into a real number system. Okay, so it means to use this second criteria is easy to use as compared to one, requires less computation, but we need to translate this into the real number system by taking the magnitude of the vector. Okay, so then we'll just easy check will is it less than tolerance or not. Okay, now taking the magnitude of the vector has a sophisticated name called the norm of a vector. Okay, magnitude is just a name borrowed from a general actually term which is norm of a vector. Okay, so we first going to learn about quickly about what is the norm of a vector. Okay, okay, then we'll continue this. Okay, we are going with this criteria number 2, that either we get a solution or not. We can also use a criteria number 3. Okay, it's relatively one more calculation than the 2, but we can use it. Okay, but not as much calculation as we need to do with the first stopping criteria. Okay, norm of a vector is denoted by, so if for example x is a vector, and if I want to take a norm, so it is denoted by this. Okay, this is the notation. Okay, and it is a function which takes the elements of Rn to the non-negative reals. Okay, so when you take a magnitude of the vector, it's always non-negative. Either it is 0 or it is greater than 0. Okay, magnitude is never negative. Okay, so a distance, magnitude is a distance. Okay, so it is not a negative value. Okay, so it means magnitude is a norm of a vector. It satisfies this condition. You can define, by the way, any particular criteria. Okay, so there are two famous norms. First is called a two norm, which we usually learn as known as the magnitude of the vector. Okay, what is a two norm? If you want a two norm of a vector x, so let's say this is a vector x, and you want a two norm. Let's say x is particularly this vector. So we know the definition. What is the definition? Distance from origin will be x1 square plus x2 square xn square and square root. So this is the definition that you already know. Okay. Okay. Um, you wanted to take the magnitude of the vector. You wanted to take so there is an initial guess, there is an updated answer. Okay, so we got two vectors. When we subtract them, we wanted to know either they are near to each other or not, up to 10 is power whatever the accuracy is. Okay, now to do that, we have to translate that particular vector into a real number. How can we do that? We can take as one thing which we already know, we can take a magnitude of the vector. Okay, but you know what is this? This is just the distance of vector x from the 0 vector. Okay, if I ask you just take the magnitude of the vector, it's just the distance of vector x from point 0. How you take the distance? So there is a vector x1, x2, so on to xn, and there is a 0 vector. Okay, so how you take the distance? So it's x1 minus 0 whole square plus x2 minus 0 whole square plus xn minus 0 whole square. Okay, this is the distance of a vector from another vector. Okay, another vector is a 0 vector, so this is actually this quantity. Okay, so for example, if x is 1, 2 and minus 5. Okay, and if I ask you to take the magnitude of the vector, or other name is 2 norm, take the 2 norm of the vector, it is simply 1 square, 2 square and minus 5 square. It is a positive square root value which is of 30. Okay, so it's simple. Just take the magnitude of a vector and we call it as a 2 norm. Okay, understand? You understand it? Okay, magnitude में कुछ same चीज़ है. It's the same name. It's another name of the magnitude of the vector. 2 norm. Okay. नहीं हमने अभी कुछ भी नहीं किया. We have taken the same thing. We actually derive from here. Na? If you come from here, it is the next is this thing. Okay, so it is the same thing. Okay, so this thing and this thing are same thing. Okay, there is no different mathematics. Okay. A first norm. So let me just explain. There are other norms. Okay, so let me go over there. It has a 2 norm. and I'll let you know what is a 2 norm or 3 norms or other norms. Okay. Okay, there is first is a 2 norm which is very famous. Then we have a P norm. P is represent 3 norm, 4 norm, 5 norm. Okay, so that's not that much related to us. I am going to tell you what is that. But the other famous one is infinite norm. Okay. Okay, what is an infinite norm? And it is actually represented by this notation, and this is the maximum value absolute maximum value from this particular set. Okay, let's take the same example, which was 1 2 n minus 5. Okay, if you take an infinite norm of this vector, the definition says take a maximum value from absolute value of 1, absolute value of 2, and absolute value of minus 5. Whatever the maximum value will be, that will be the infinite norm. Okay, so this is 5. Okay, so if you see out of the two, relatively infinite norm is easy to compute. Okay, okay, what is a P norm? You can plug the value of P, anything integer value. P norm is xp. We will not be using that. Okay, we'll just be sticking to 2 norm or infinite norm in our problems. Okay, but oh, so this is x1p, x2p, xnp, and power 1 over p. Like this is x1 square, x2 square, xn square whole power 1 by 2. Okay, so if you wanted to calculate maybe 3, so it's x1 cube, x2 cube whole power 1 over 3. Okay, if it is fourth norm, then x1 power 4, x2 power 4, so on to xn power 4, and then 1 over 4. Okay, but we'll not be using over this. It's too much mathematics. There are LP spaces. Okay, we're not going over there. Okay, but we'll be using the 2 norm majorly that you already know, and the infinite norm is just the absolute maximum value from the vector, from the given vector. Okay, so easily we can understand this way. Now, by the way, you can also define any norm. You can, if you can do that, just this is the condition. Okay, it can be anything, but it should satisfy this particular procedure. Okay, so you can take any vector to positive non-negative reals. If you can develop any particular way, a general way, then that can also be considered as a norm. Okay, we have a question. Relation this particular, so it's just a function. It's just a function that takes values from Rn to positive non-negative values. For example, if you have from R2, if you just make the y-axis as 0, what is the projection? You take the projection on x-axis. Okay, so you take from R2 to R. If you just put an absolute sign, then you will get the positive projection always. The positive numbers will also be projected, the negative numbers will also be projected on the positive x-axis. Okay, yeah, we are reducing the dimensions, and we are just taking that vector to the real number system. Okay, okay, okay. Now I'll take an example to actually explain this two methods. So we have built most of the things that we need. So let me just write an example. So use fine. uh, so let me just write an example and we got 17 here, and then we got. Okay, you see, you can just relate this question with the question we have in the method topic 1. Okay, there is a problem, there is an accuracy to achieve, there is some initial guess given. Okay, so we'll start with a thing which is very much required. That is, what is an iterative scheme that we have to build to find the solution at the first step, if this is the solution at the initial step. By the way, capital X is what? Capital X in this particular problem will be x1, x2, x3 and x4. Okay, so this is the value of x1, this is the initial value of x1, this is the initial value of x2, this is the initial value of x3 and this is the initial value of x4. Okay, we got 4 sequences, subsequences. Okay, so now let's go to the procedure of the Jacobi method. Step number 1. So this is a problem. So write x1 in terms of other variable from the equation number 1. So if I do that, x1 will be 17 by 7 plus 2 by 7x2 or minus 1 by 7x3. Okay, so if I write x1 in terms of other variables from equation number 1, this will be the form. Then if I write x2 in terms of other variable from the equation number 2, okay, so x2 will be, okay, then we have then we have okay, please do check if I have made any mistake. Okay, minus 1 over 9. Okay, so if I write x2 in terms of other variable, just from the equation 2, I'll find this way. If I write x3 from the third equation, okay, it will be 15 by 10. Then I got minus 2 over 10 x1, and then I got minus 1 over 10 x4. Okay, and if I follow similar pattern for the last equation, so x4 will be 10 over 6, then minus 1 over 6 x1, then plus 1 over 6 x2, and then minus 1 over 6 x3. Okay, there is a difference. Okay, it's okay. Okay, so we got the relation x1 in terms of other variable and x2 and x3, x4 from the first, second, third, fourth equations respectively. Okay, now the initial value of x1 has been given as 0. Okay, so this is x1 initially, this is x2 initially, so superscript is representing an index notation. if you just try to understand this way, this is actually the initial values of x1, x2, x3. Now, if I use, just consider these equations written into a computer system, okay? If you write anything into the computer system, it will just evaluate the things on the right hand side and assign it to the value which is on the left hand side, okay? So just use the value of x2 and x3 initial values over here. If you use those values, they are 0, okay? What is the answer we got? 17/7. If I plug over here, we got minus 13/9. If we plug over here, we got 15/10, okay, or 3/2. Or if I plug over here, it will be 5/3, okay. This is the answer I got, okay. Now, these are the updated values of x1, x2, x3, and x4 respectively, okay. So let me write over here x1, and I got an x1 in a way that it is 17/7 minus 13/9, 3/2, and 5/3. Now I need to check, is it a solution or not? Okay, now that's the point comes of using the norm. Okay, so I need to check, is it a solution or not? How can I do that? I can subtract x1 and x0 because it is the previous answer and I just found this one. Okay, there is no other information we have. Okay, so what I'm going to do is I'm going to take a norm of this vector. हाँ, हमने जीरो किया है of every value. First में हमने x2 और x3 को किया, okay? Because but is the initial value of x2 and x3. Just pick the values from here, okay? So if you plug over here, so the answer is over here. If you plug x1, x2, x1, x3, and x4, the answer is this, okay? If you plug x1 0, x4 0, answer is this, and if you plug these value, answer is this, okay? So just a simple, just use these values on the right hand side. Okay, this is the magnitude that we need to compute, okay? And we can start with, let's say, 2 now, okay? So we can either in a particular question use a 2 norm or we can use an infinite norm. We can't switch to every iteration, okay? So I have calculated this. It will be what? It will be 17/7 square plus minus 13/9 square plus 3/2 square plus 5/3 square under the square root, because the other vector is a 0 vector, okay? So if I compute this, this comes out as 3.608, okay? So there is a difference, then there is a norm, okay? So there is a difference, then there is a norm, okay? Otherwise it can be negative, no? Otherwise it can be negative, okay? So you just have to take a difference of the vector, then take a norm, okay? Okay, so this is 3.608 and it is obviously a greater value than 10 raised power minus 3, which is our tolerance, okay? This is the tolerance we wanted to achieve, okay? So it means we don't got a solution. Let's go towards finding the next values of x1, x2, and x3. Now in this scheme, we are going to use rather than that x naught, we're going to use these values. Okay, this is the value of x1, this is the value of x2, this is the value of x3, and this is the value of x4. We're going to use on the right hand side. If we do that, okay, so if I plug the value of x2 as minus 13.9 and the value of x3 as 3/2, I got the value of x1 as 1.8, okay? If in the second equation I use the value of x1, x3, and x4 as mentioned in over here, we got an answer which is minus 0.86, okay? Then I have 0.85 and we have 0.77, okay? So let me just write the things over here, which is I got x2 1.8 minus 0.86, 0.85, and 0.77. Anyone, what is the stopping criteria? Just take the difference of the vector you have with the vector which is used as an input. Okay, so x2 minus x1 magnitude or a 2 norm. Okay, if you calculate this, it comes out as 1.4021, which is not less than 10 raised power minus 3. Okay, so you see the process is simple. A calculation is easy. Okay, not a very difficult process. Okay, so similarly you will compute x3, you will compute x4. Okay, and you have to go up to the tolerance, we get a solution. Okay, so it will be a homework for you. Just complete this. You will get the answer in 7th iteration. Okay, and the answer is 2 minus 1 1 and 1. Okay, you'll be able to get this answer in the 7th iteration. This is a homework for you. We did the 2 iteration, you can do the remaining ones. Okay, now the thing is, I don't see in a very good manner this problem has been posed in form of iterative schemes. Okay, so let me do that. So if I calculate the first iteration, let me just restart a problem. Okay, if I, this is the initial guess, and if I use this particular scheme, okay, then at the first iteration, what is the values we used? We use x2 at the 0 step, x3 at the 0 step, and what we got, x1 at, x1 has been given at the first step. The value of x1 has been updated from the first equation. Now the second equation update the value of x2. So if this is at the 0 step, this is at the 0 step, we'll get this value at the first step, next step. Okay, so a similar observation we can plug into the remaining equations. Okay, okay, so if you just wanted to generalize it, if this is the information at I minus 1 step, you get the answer at the ith step. Okay, if this is the information at 0 step, you calculated the 0 step, you got the information at the first step, then the index will be I is equals to 1 on the right hand side. Okay, then you get the information at the second step. Okay, so that's how you will proceed. Okay, so if I just try to generalize it, it is, if it is I minus 1, what this index will be? I. Okay, this will be I. So you can, let me just write I minus 1. We get it I. Okay. Okay, it means you will get, when I is equals to 7, you will get an answer. Okay, we just calculated I1 and I2, and you can just keep continuing. Now, this is the scheme that we have. Okay, so I start from 1 to onwards. Okay, whenever you get a position where xi minus 1 magnitude or the 2 norm is less than tolerance, that is the point where to stop. Okay, so that will be the point. Now this is a Jacobi method. Okay, now let's try to improvise this. Okay, we'll just the method is over here, we'll just try to improvise it in a way that hopefully you will be able to understand yourself. Okay, let's try to discuss this. Okay, and okay, so we got x1 क्या हुआ चलिए ठीक हो गया so so we got the solution at the initial solution is 0 0 0 0. Okay, let me write in a column form so we'll able to understand it easily. Okay, so these are the values of x1 x2 x3 and x4. Okay, so now if I use those values, so we just restarting a problem again. Okay, and we with a focus that we try to improve it. Okay, so if I just use this information at I is equals to one step, okay, if I plug I is equals to 0 1 over here, the information will be at the 0 step. If I plug x2 value 0 and x3 value 0, what will be the answer? 17 by 7 as we found in the previous calculation. Now let's try to calculate x2. When we are calculating x2, do you find any information that has been updated? If you see this particular value or these two values, what is the difference between the two? As we just said, x1 has been updated. So you see the value of x1 can have two options. Either we can choose 17 by 7 or we can choose the value from the previous step. Okay, in this particular step we already have updated the value of x1. Okay, so we have an option that we can use the updated value of x1. Okay, but we have no option for the variable x3 and x4, so obviously we'll use the only option we have. Okay, so let me just write, rather than I minus 1, I can use the index I, and if I use this, okay, I will get the updated value of x2, which is minus 1.17. Okay, this is the value I got. Now when I'm calculating x3, you know, two variables has been updated, x1 and x2. So x1 has been updated, so I can use the ith index. x2 is not involved with the coefficient of 0. Okay, so x4 is not been updated, so we'll use the I minus 1 index, and if I use this in the first step, the answer comes out as 1.01. Okay, yeah, 1.01. Now in the final step, you can just see it's an easy observation. X1 has been updated, x2 has been updated, actually all the variables has been updated. Okay, it's a final equation, and final equation is giving me the last variable. Okay, so all the values we're going to use is 17 by 7 minus 1.17 1.01 rather than 0 0 and 0. Okay, so if I do that, the answer comes out as 0.9 for x4. So this is the answer I got at the first step, which is 17 by 7, or another way we can write 2.43 minus 1.17, 1.01 and 0.9. Okay, this is the answer we got if we just improvise the Jacobi method. Okay, if we just improvise the Jacobi method, the stopping criteria is same. It's x1 minus x0. You have to check the difference between the two and take the norm. If it is less than tolerance, you need to stop. Okay, so if you just do this particular problem, you will get the answer in the fifth iteration, and answer is same as we have already told you. Okay, that is 2 minus 1 1 and 1. Okay, so please complete this problem too. This method is called a Gauss-Seidel method. Okay, if you update the values of the variables, you find this is called the Gauss-Seidel method. Otherwise we use the Jacobi method. Now a last couple of things and we'll be over. Okay, that is uh, a simple thing that not it will not take much time. Okay, so it is either we'll be able to get to the solution every time we use the Gauss Jacobi method or a Gauss-Seidel method. The answer is no. Okay, the answer is no. It is not always possible to get a convergent sequence. Okay, So to answer this, let me just go back to the slide. You can see it is a strictly diagonally dominant matrix. You have already learned this somewhere in your knowledge of the matrices. Okay. So let's see what is a diagonally dominant matrix. Okay. You see the definition. Okay. Let me just tell you in a way that we are talking only about the coefficient matrix A. We're not talking about the right hand side B. It is only the coefficient matrix A. A matrix will be diagonally dominant if you, for example, you start from the first entry, first diagonal element, main diagonal element. If you take the example we just have, okay, this is 7 minus 2, 1, 0. Then we have 1 minus 9, 3 minus 1, 2, 0, 10 and 1, 1 minus 1, 1 and 6. Okay. So if you go to the definition says pick the first diagonal element, okay, take the absolute of that point. A11 is 7. If you take the absolute, it will remain 7, and just add the absolute of all other numbers in that row. Okay, so if you see the row number 1, if you add it, it's minus 2 plus 1 plus 0. Just take the absolute of every number in that row and sum it up. So answer is 3. Okay, now this element, which is a diagonal element, should be strictly greater than the sum of the other numbers in the row. Okay, so this 7 is greater than 3. Now come to the second row. What is a diagonal element? If you take the absolute, we got 9. If you add the numbers, what is the addition? It's 5. Okay, so this element is greater than the sum of the other elements in that row in absolute terms, so it is greater. Okay, if you see the next diagonal element, it is 10. Okay, it is 10, and if you take the sum, it is 3. Okay, and finally A44 is 6, and if you take the sum, it is 3. Okay, so just see this theorem, and it's easy to find. If you have a diagonally dominant coefficient matrix, okay, then the Jacobi method or a Gauss-Seidel method, both will converge towards a solution for any choice of initial guess. Okay, you can take any choice, it will take you towards a solution. Okay, so this is the condition of the convergence condition for the Jacobi and Gauss-Seidel method. By the way, this is a sufficient condition. There are two types of a condition: sufficient and necessary. Necessary means that if, for example, in this setting, if A is a coefficient matrix, then it will be divergent. That is the only option. Okay, what is a sufficient condition? It says if A is diagonally dominant, then the sequence will be convergent. But if, for example, A is not a diagonally dominant matrix, okay, then might be it converge, might be it not converge. If it gives an option that otherwise maybe it converge or diverge, then it is a sufficient condition. Okay, otherwise it is a necessary. By the way, it is a sufficient condition. Okay, so it's a simple condition to check from the matrix. If it is a diagonally dominant, then you can then the Gauss-Seidel and Jacobi method will always converge. Okay. It means you don't have to worry about the initial guess. Okay, you can take any initial guess, it will take you towards the solution. Okay, let me just write if this is the coefficient matrix. Okay, if this is the coefficient matrix, is it diagonally dominant? Okay, you see a 1 and there is, you got a 4. Okay, Can we make it diagonally dominant? We can swap the rows. Which swapping of the rows will be a wise? So swap rows 1 and 3. Okay, if I do this, I got 4 1 2, and then I get 2 1 4 1 3 1. Now if you see, here we get a 4, the sum is 3. This row we don't have to worry. If you come to the second row, this is 1 and this is 6. Can we do something more? We can swap the last two rows. Okay, please don't now move with the row number 1. It's stick there. Okay, it's stop. You don't have to now move it. Okay, so if I swap now rows 2 and 4, sorry, 2 and 3, it is 4 1 2. It's a 1 3 1 and 2 1 4. Okay, now it's diagonally dominant. Okay, so it means if the coefficient matrix is not diagonally dominant, at times we'll be able to make it diagonally dominant, but it's always not true. Okay, still there are coefficient matrices which are not diagonally dominant. What can we do with that? So we can use two things, namely, there is another method which is called the SOR method, successive over relaxation methods. That's not part of our course, so we're not going there. But I'll let you know, it is the generalization of the Gauss-Seidel method. Okay, that methods are used to deal with that particular scenario. Other thing is that that we can actually go back to the direct methods. LU factorization or a Gauss elimination. Okay, so we have to make an adjustment to do. There is another technique which is a scaling. Okay, I'm not going over there, not part of our actually course. So, but just to conclude now, to particularly this lecture, we able to know what is a norm of a vector, how to take a norm of a vector, how we have developed the techniques for the Jacobi and Gauss-Seidel method, and we learn about the theorem which tells about that if A is a diagonally dominant matrix, strictly diagonally dominant, not diagonally dominant, strictly diagonally dominant. Okay, what is strictly? Strictly means strictly greater than, not equals to. Okay, it can't happen that if the diagonal element is same as the sum of the other element. Equality is not possible. It should be strictly greater than. Okay, so that's why it's called a strictly dominant matrix. So we learn about the convergence criteria, which is the coefficient matrix should be strictly diagonally dominant. Okay, thank you so much.